I just let a humanoid robot live in my house for 2 days. His name is Neo, and he was created by a company called 1X. I sat down with one of Neo's creators, Jang, the VP of AI for 1X, in my living room to ask him some questions. Before working at 1X, Eric did research in neuromorphic computing and was an early member of Google Robotics Lab, all of which we talk about.
And I came to the realization that the algorithms were very general. They probably would scale to actually general purpose robots and doing things in the home and solving all kinds of tasks.
We're here, not in the HQ of 1X Technologies in Norway or San Francisco, but in my apartment, because for the immediate follow-up episode of this S3 episode, 1X was kind enough to bring Neo, their latest humanoid robot, here to my apartment and let it live with me for a few days to see what it's like. It's in an early beta R&D stage still, but it is beyond impressive. And I'm sitting here with Eric Jang, the VP of AI for 1X, and we're going to talk about all sorts of things related to AI and robotics. Thanks for sitting down.
Thanks for inviting me to your home, Jason.
This is true. I forget this is my home. I'm not used to filming these in my home. Normally we're like in a factory. It was like yesterday, filming-wise, I sat down with Bernd to talk about all things robotics, sci-fi stuff, and the current state and the future kind of 5-10 years and manufacturing goals of 1X. But for people who haven't watched the main episode yet and should, can you give a quick kind of primer on what 1X is and what you guys are up to?
Sure. 1X is a humanoid robot company that is making safe and capable and affordable humanoids for the home, so that we can do all kinds of tasks like laundry and kitchen and helping their grandparents move heavy furniture when they have their friends over, and basically any number of tasks that we can scarcely comprehend to think about today.
In my apartment, it did, if you haven't seen the main episode, it helped me cook. Like it got stuff in the fridge while I was cooking, handed me eggs, which was super impressive. They were not hard-boiled or fake, they were like actual real eggs, and helped me do laundry, and then just sort of entertain some like friends I had over, and it was like, I don't know, it was really, really cool. And it was like insane just how smooth the robot moves. Have you always been interested in robotics, or what was sort of your origin into joining 1X?
Yeah, I've always been interested in science fiction, robotics, AI, the idea of what does it mean for a living thing to potentially be not made out of flesh, but metal, and what are the implications of those like philosophically, and that's always been fascinating to me. So growing up, I watched a lot of cartoons like The Iron Giant. I've seen pretty much every recent AI and robotics movie like Ex Machina and Her and everything in between. I love them all. They're all sort of interesting in their own way. And yeah, I think a lot of roboticists derive their inspiration from movies and fiction.
I want to ask you more about fiction and sci-fi later, but I'm curious about what you were like interested in as a kid. Like today, you are, I would call you a roboticist. Maybe you'd be like, no, I do the AI and the software side of it, but you're still a roboticist. And in my mind, were you always interested in the robotics aspect on a working level, or what was kind of your childhood through college and first job kind of journey like?
Yeah, I had a pretty interesting set of experiences job-wise. So in high school, I did a lot of science fair competitions, and the topic I was super interested in at that time was, is it possible to live forever? People like Brian Johnson are really interested in from the human biology standpoint today, but I was really interested in high school going down this rabbit hole of telomeres and telomerase and animals that can potentially live forever, like hydras and cancer cells and things like that. And I studied that for a little bit in high school. I volunteered at a lab where I did a bit of telomere research, and yeah, it's really cool. But during that time, I came to realize that I was no good at biology research. I was asked to do this pipetting of this 96 well plate, and basically the idea is you're going to copy this little pipette of liquid from one batch of tubes into this plate, and then you put that plate into a machine. And I would somehow keep fucking it up. And I wasted 5 plates worth of experiments on this. It's a very simple, monotonous task of doing one tube to the plate. And I just couldn't get this right because I guess I'm not good at paying attention for a long period of time. And it was around that time that I realized that okay, maybe this biology thing isn't quite for me. I'm a little bit better at computers and things where I don't need that insane focus. And, incidentally, I do think actually this is one area where robotics can have a huge impact in ways that we can't even imagine today. So, for example, a lot of biology labs today are run by grad students, and science could progress a lot faster if we had robots actually doing the pipetting and carrying the outputs of one machine to another machine. Biology often is thought about as a series of very specialized machines doing science, but you often need something like a humanoid to carry the outputs from one machine to the next, or open up a lid and stir the bacteria inside.
I mean, a lot of people would argue that like you definitely don't need a humanoid to do that. Like a gantry is sufficient, but I don't fully agree with that argument. Or I agree that like there are more efficient systems than humanoids for manufacturing. Like, okay, you need to move a thing on X and Y. But in general, it would be great if we had humanoids that could do that too.
Yeah.
And so I guess one thing I'm curious about is like, and I asked Brent this yesterday, is like, why has 1X has your whole team bet so hard on humanoids? Because this is not a recent new thing for you guys. This is like the foundation of the company. And it's not just part of the latest Silicon Valley hype cycle of it. Like you guys really have conviction over this.
For sure. I have a series of research experiences when my time at Google that completely convinced me that humanoids are the only hardware form factor that makes sense for both doing tasks and also even maybe forming human level intelligence. I think there's often a dichotomy presented about specialized machines versus generalized machines like humanoids. Some roboticists say like, okay, instead of having a humanoid in a lab, we'll just build a gantry system that automates medical science or something. But I think that's a false dichotomy. I think the future of automation is going to be a bunch of very specialized machines like, your laundry machine or some PCR machine. And the humanoid is a glue that actually connects all these pieces together so you can actually run the whole scientific process.
Well, and also there's sort of the data side of this, right? That like Burton talks a lot about like data is sort of our whole world of data, especially for training AI, is built around humans.
If you want to train a machine to think like a human, you have to have that machine see everything that a human sees, from childhood to adulthood to pretty much every circumstance a human would encounter in their natural life. The internet is a source of a lot of this data. Lots of people spend time on the internet, but there's also a lot of other kinds of data that are not really easily accessible on the internet. So yes, it's possible that you can get quite close because there is a lot of information on the internet, but at the end of the day, there's a lot of knowledge around how people do things. For example, can you find on the internet detailed instructions for how to actually move your fingers in a way to turn the pages of a book? Not really. It's not really like captured in a very easily accessible way. In our view, the best way to actually access that knowledge, for which the tactile world has a large amount of this stuff, is to just have machines out there collecting what it is like to be a human. And once you have that, then you can build intelligence that's very closely matched with humans, since the data is so closely matched to how you're actually trying to deploy it.
And it's sort of the data engine idea, just like with self-driving cars and Tesla, their approach of putting cameras on all the cars for years and training these models. And I want to ask more about 1X's approach to that. But I also want to jump back to talking about your doing bioresearch and like, okay, this isn't for me. I think I like computers more.
Yeah. So after bioresearch, I was then the next question is like, how else can you make an immortal thing? So the next way to do this is maybe you could simulate a brain in a silicon computer. And if you can upload brains to silicon computers, then you can keep a brain alive forever in practice, right? So the next topic I got interested in around my senior year of high school was neuromorphic brain simulation. And so I had the honor of being able to volunteer in Kwabena Bohan's lab at Stanford, where I basically just learned sort of my first beginnings of how to do programming and sort of neuromorphic simulation and computational neuroscience. And I'm super grateful that he took me in and like taught me a lot of what I know today. And the basic idea of neuromorphic computing is that you want to simulate the biophysics of a neuron, not in a petri dish, but in silico, in a computer simulation. And there's a lot of neurons in the brain. There's a lot of synapses. So simulating this with a normal CPU is virtually impossible. Even if you have a GPU, it's also very difficult. So the idea was to basically build a custom chip that could simulate a lot of these neurons and connections very quickly. Around that time, I came to realize that the software framework for building useful capabilities out of these brains was still pretty limited. We were trying to implement a simple robotic controller where we translated a robotic control algorithm into this neuromorphic framework and see like how could a brain potentially represent the control of moving an arm or something.
Were you doing that virtually, like the robotic simulation part, or was this like a physical?
Yeah, it was all virtual. Later, long after I left, they figured out how to do it on an actual arm.
Wow.
Yeah. So it's this idea of you take this framework about how neurons might do computation, you work really hard and you implement some robotic controller using that framework. Unfortunately, these kinds of methods are very hard to get working because you're trying to shoehorn a classical software abstraction into a set of biological circuits. It's almost like trying to emulate the Windows operating system in a in a flesh brain, right? It's like, yeah, in principle, a human brain can do all those calculations and emulate a computer, but it's not really the right fit for like how you do it. Like humans and animals, they probably are not inverting matrices when they are doing stuff. And one of the things that we were trying to figure out actually in this lab was like, how do you invert a matrix with neuron simulation? One other thing I realized in college was that unless you were using neuromorphics, it was impossible to simulate a large number of neurons and synapses in real time. So if you want to build a robot that lives among us, its brain has to run in real time. You can't run it in slow speed. So you can do the napkin math of like how fast CPUs are. And if it turns out you cannot really simulate more than like 1 million neurons and then the sort of 1 billion connections, or I guess, sorry, what is that? 1 million. So I guess 1 trillion connections between those billion neurons. It's just kind of hopeless at that point. Your computer can't simulate it fast enough.
And no dumb questions here, but like you couldn't just add more CPUs or build a bigger kind of supercomputer to fix that problem, or it still just doesn't scale properly?
You can build a supercomputer to try to tackle this problem, and people have actually tried to do this. But it as a sort of college student, we don't have supercomputers, so like I wanted to kind of do something useful, and it was kind of depressing to me that my laptop couldn't simulate any meaningful number of neurons. And also, if you think about it, like a supercomputer consumes so much more energy than like an animal that can do all sorts of things, right? So clearly something's not quite right about this way of doing things.
Well, it's pretty cool that you say that, to like interject for a moment, because I haven't brought up like what is behind you, or like we obviously asked it to be there because it like looks cool. But can you talk about like what's behind you on the screen here?
Yeah, this is a supercomputer running a sort of a brain simulation, except this is with deep learning. So it's a form of machine learning that is loosely connected to simulating neurons, but much more efficient than today's methods of doing a biophysical simulation of neurons. So in a biophysical simulation, you would try to actually simulate time, for example, like at the millisecond level, and to get 1 second of activity, you would have to step through 1,000 milliseconds of simulation. Whereas in deep learning, there's no abstraction of physics. It's really just like a bunch of units that compute based on what's given to them. So over the last 10 years, deep learning has really emerged as the most effective way to use data and get capabilities out of it. In principle, other ways of doing computational neuroscience can do this too, but even today, computational neuroscience methods can't recognize all the digits in ImageNet. I'm sorry, all the classes in ImageNet, for example, whereas this is a sort of trivial task for most deep learning methods.
And for clarity, this is a random training set, or this is related to 1x?
Yeah.
Or what is going on here?
So what you see here is our H100 node training one of our world models. And what a world model is basically analogous to a prefrontal cortex in a human. So the prefrontal cortex in people is designed to basically anticipate the future. Humans evolved a very large prefrontal cortex because we save energy by anticipating what happens in the future, so we don't actually have to encounter situations that would expend a lot of energy. And we can also, avoid moving if we know that something is going to come to us, and that's why having a brain that can predict the future is really energy efficient. So modern machine learning methods take a very similar idea where, in LLMs, your goal is to basically predict the next word. And similarly, for robotics, you can build a similar prefrontal cortex where the idea is to predict what happens next, given what I've seen so far. If you build a brain like this with deep learning that can anticipate the future, it extracts general knowledge about the world. Because in order to predict the future, you have to understand quite a lot of things about how the world works. For example, if you're looking at a person doing something, in order to predict what you're going to see them do next, you kind of have to have a pretty good theory of mind of how people work. If you're doing some task, you need to also predict how the world responds to your actions. And all of that knowledge together makes it very possible to build a general purpose intelligence from a large amount of data, which is what we're doing at 1x.
Very cool. So back to kind of talking about neuromorphic, what did you call it?
Neuromorphic
computing, yeah. So what happened once you kind of were done with your time at this lab?
Yeah, this was a summer volunteer project that I did at the lab, and then I went to school where I wanted to major in neuroscience because I thought, okay, like I want to learn more about how you simulate brains and become immortal.
And this immortal thing is like really like, yeah, you keep coming back to this. So this is really like what age, like what was your sort of going on in your life, and where was your brain at when you decided like, yeah, okay, I really want to like really think about this quite deeply?
I remember like the experience of how this came to be. So I was in 8th or ninth grade learning about science fairs and thinking, okay, like I want to do some science fair stuff. Like, what are some cool ideas of science fairs? Like this is literally what I Googled.
Immortality.
Yeah, and Immortality sounds like a fun science fair project. No, but the way I ran into this was just clicking around random Wikipedia pages, and then I guess I learned about the notion of senescence, which is like most cells can't live forever; they actually die at some point. And there are actually some animals like hydras that their sort of cell line, which is basically like one consistent set of DNA, more or less can perpetually replicate without any sort of limit on how many times they can replicate. Whereas most mammals, all mammals, I think, to my knowledge, and larger organisms in general, cannot do this. So that was something that was super interesting to me, which was like, yeah, why can some animals live forever and other animals, they can't really do that? And then the sort of natural follow-up question is like, yeah, like sort of as an engineer, if one set of animals has property A and another set of animals doesn't have that property, to really understand that, like, you kind of want to show if you can transplant that property to some other set of animals. It's like that quote from Feynman, like, what I cannot create, I cannot understand.
Very cool. Okay, so you're back to school now.
So yeah, in school, I thought I would major in neuroscience. Brown is a very liberal arts school where you can basically take whatever classes you want. So I went to like a neuroscience seminar, and I found it incredibly boring because it was just like textbooks and you're memorizing stuff they taught in neuroscience for the last 10 years. And what was way more interesting to me was like the computer science aspect. So throughout college, I mostly did computer science and math. And in terms of jobs, I worked at Pixar a little bit. I think I like the idea. It connects to what I'm interested in because the notion of imbuing some sort of non-living object with life is really something that the animators and the art community do really well. And so I thought that animation was super cool because you could convince people that something is alive when it really isn't. And that's kind of what we're trying to do with robotics as well.
What'd you do at Pixar?
I was an intern for one of their sort of mentee programs, basically where they teach you the ropes of how they do the pipelines. I didn't do any shows or anything, but it was a great experience where I learned about like, yeah, what is it like to be at Pixar? What are the different departments? And yeah, it's great. I'm still friends with a lot of people that I met there.
Huge. Okay.
And so after that, I went to Google to do a sort of your classic Google internship with the beanies and the little spinny things on top. Yeah, so after the sort of typical software engineering internship, I was like, okay, let's do something a bit more highbrow and mathy. So I went to Two Sigma to do like a quantitative software engineering internship where kind of you look at extremely large numbers of money on your computer terminal and you try to make those numbers go up. And so I learned a little bit about portfolio optimization there, which is completely unrelated to like artificial intelligence or life or robotics or animation, but it was just kind of like a cool trajectory that was, potentially lead to a very, very nice career. But I did learn that like, while finance is very interesting and I can totally geek out about all sorts of finance things, I didn't see myself doing that long term in my career. I just wanted to like go back to doing something. I think that's the mix of fun, challenging, and also meaningful for humanity. And so I think robotics is a better fit for that.
Very cool. And so, yeah, how did that lead up to you joining Linux from where you are post-finance job?
So at Google, I spent 6 years doing research on many kinds of ways to teach robots to be smart. And so this involves things like scaling out data, using reinforcement learning, thinking about how data affects generalization, also thinking a little bit about more core machine learning methods like generative modeling, which is basically like how do you generate realistic pictures of faces and things like that, which actually intersect really closely with robotics, more so than most people think. It was that time that I sort of formed my core framework about like how to do general purpose robotics right. And this involves basically what we see today, where you scale up a large amount of data, you find some sort of neural network that is like a data sponge, and you just train the data sponge on all this data. And once it has absorbed all the data in a very efficient way, then it has essentially become a prefrontal cortex, like what I was talking about earlier. So the prefrontal cortex, you can think about it as soaking up a lot of information and trying to make sense of it. In fact, your brain is doing this all the time. So when you dream, you kind of see some nonsensical things show up in your brain, and that's because your brain is trying to sort out like and make sense and explain everything you've seen as in a coherent way. And so that's the basic framework that like I kind of worked on when I was at Google. And I came to the realization that the algorithms were very general. They probably would scale to actually general purpose robots and doing things in the home and solving all kinds of tasks. But the limitation at that point, I think, was hardware. So if you don't have a form factor that can move as smoothly, as quietly, as safely as a human, you just can't deploy the system and collect data in the places that you would eventually want general purpose robots to show up in.
Before asking more about now what you're working on at 1X, I'm still curious, like what exactly those 6 years working on robotics and things related to it at Google looked like. Like, were you working with much hardware? Was it fully on the software side? Like, how much can you share there?
Yeah, it was fully on the software side. So the hardware was basically provided by various sub-teams had different hardware, but I was mostly working with mobile manipulators that were made by Everyday Robots. Everyday Robots had a lot of very talented hardware engineers who built a decent robot that was like a small car with a tower. There's a camera on the tower and an arm sticking out of the tower. So this is fine if you're trying to do tasks like drive over to some completely unobstructed area, then pick up something, and then drive over somewhere else and set it down gently. But if you really want to go to the full set of tasks in a home, that's not going to work. For example, if we look at this room here, that base would not fit in any spot here.
Yeah.
Right? And so if someone is coming here trying to look for things or tidy up the space, they would have to basically clear the whole room before they could even do anything. And that's like the entire point of a household robot is to clear the room in the first place.
Right.
So I think a lot of people in robotics who want to build general purpose robots really have to go all the way to the humanoid form factor for something that actually works. I think this is still something that's extremely non-obvious to most roboticists, but mark my words, I think in like 3 years, everyone will be using humanoids.
Well, it's really interesting, the lack of sort of faith around humanoids. Like, for example, I have a talented friend of mine who's an ex-roboticist, now works in manufacturing. And he made me, like when we were planning this 1X episode, like, okay, I told him 3 months ago before we were doing it, 1X's new humanoid robot that you don't know exists is coming to my apartment. It's going to fold laundry and all this stuff. He was like, you're crazy. I'm sorry. You're kind of smart. You're not a roboticist like I am, but you're wrong about this. And I was like, oh, I've seen it. I will take the bet that it'll work. And so we put like a real monetary bet on this. And I was shocked by how, like at the time of the filming, we actually haven't done the demo yet, so I could be wrong still, but I'm still very confident that it's going to go well. And I'll update the result here below. But he was so convicted about this. And you talk to many other roboticists, and like you said, that like this is sort of a common reality right now, that like there's still a ton of doubt around humanoids. Can you sort of like share why you think that is?
I think the skepticism around humanoids comes from a very long history of roboticists seeing these very high expectations promised by entrepreneurs and visionaries and futurists. And then when you kind of go and watch the reality of where robotics actually is today, it's very disappointing. So, for example, you can go on YouTube and find this 8-hour-long video of the DARPA Robotics Challenge, which is like this several teams of robots having robots go through some door, go to some wall, drill a hole in the wall, turn a valve. A human would probably take, like a firefighter would probably take less than 60 seconds to do all this, maybe 30 seconds. And some of these robots were running this for like an hour. You know, this is a very, very long sequence that was it's almost kind of funny to watch because there's people sitting in these stadiums watching these robots move extremely slowly, right? So there's a huge gulf between what maybe you might see in a sci-fi movie and what actually was there. Now, since 2015, the roboticists have made a lot of progress. And I think there's been 3 really major unlocks that have been quietly happening and not really noticed actually by a lot of technologists, especially in Silicon Valley. The first one is that actuation technology has become geometrically cheaper over the years. So what does a robot arm cost? Well, an industrial robot arm is like a KUKA Iwa is probably $200,000 or so. And, you know, that's very expensive. You wouldn't want to buy 4 of them and combine them together to make a humanoid robot because that it would not be that useful and it would be very expensive. Right? So there's a sort of bias that many roboticists have, which is that you want to build something that is kind of cost effective and gets the job done that you want. Because to build a full humanoid, there's this idea that it would be so prohibitively expensive that it would just be not worth it. Mm. The second point of skepticism is that the software isn't there. So, you know, there is no good control theory for how you actuate both the heavy leg, the medium heavy arm, and the light fingers all in the same framework because the dynamics are so different at different scales between all these components. Not only do people not know how to do grasping reliably, people are saying like, okay, well, if I can't even pick up an object, what's the point of trying to control all the degrees of freedom in a hand, right? Like, why not just simplify the problem to something that we can have some hope of solving? So I think that's also been an idea of skepticism. And the final one is that this idea that a lot of software engineers have, which is let's build the simplest possible thing that just gets the job done. It's practical. It gets the sale done. The customer wants a simple thing, not a complicated thing, right? Like there's this Silicon Valley mindset of like build what the customer needs and not what you think is a beautiful solution. So I think those are the three like camps I would say of skepticism. So the three things that I think have changed is that, yeah, actuation technology has gotten a lot cheaper. What used to cost $200,000 now is now less than $5,000 from China. And in a matter of years, we'll probably see humanoids that cost under $40,000 and this is already cheaper than most robot arms, like standalone robot arms by themselves, right? So like we don't really fully comprehend how cheap it will be to actually make 4 limbs and all the hands and fingers together. The second part is that on the software side, the ability to make general purpose software systems that can do many, many tasks is now possible, thanks to things like machine learning. And we see this very clearly with systems like ChatGPT, where on day one, you don't just have one skill, you have millions of skills. And so when you have a software system where it is so general that it can do so many things, it then justifies using a hardware platform that is very general, right? If you're living in a world where you can only add one capability at a time, then a humanoid may not make sense because if you're adding one skill every year, then after 10 years, you have 10 skills. And maybe a humanoid isn't the best way to do that. But if you're adding 1 million tasks every year, then actually that from a hardware perspective, a humanoid is probably the right future-proof design for that kind of software.
Cool. Oh, sorry. And
the third one, I guess, is like this idea of like, let's build the simple thing and bootstrap our way up, right? I do think that there's a history of robotics companies that have tried to take that strategy where you build something incremental and you have some larger ambition to scale up to something more general. But for whatever reason, and this might be more of a people and organizational issue, many of these companies never actually get to the general thing. They seem to just get stuck in whatever automation solution they're building for their customer, and they never go beyond to the more complex system.
How did you then end up from this kind of general theory you started developing yourself at Google to joining 1X?
Yeah, so I myself thought that humanoids were far away. And so when I was thinking about leaving Google and I met Bernd, and I was completely blown away by how advanced the humanoid was. It was substantially farther along than what I thought was possible.
What year is this?
This is 2022. So he showed me a demo of Eve doing Tele-op, and it was a completely quiet robot, right? Like I didn't hear any sound coming out of it.
It's mind-boggling.
It moved extremely fast. And this is, in hard tech, often the simplest to explain things are the hardest things to make. So, in semiconductors, there's this thing called ultra pure water, which is just very clean water. Extremely hard to make. You need to build basically a huge factory to like make ultra pure water.
Correct.
One analogy I heard from an Intel engineer is that ultra pure water is to distilled water, which is the kind of water you didn't have in science class, as distilled water is to sewage.
Yeah.
That's the level of like purity we're talking about in terms of orders of magnitude. So yeah, like everyone understands what clean water is, but like to make really clean water, it's like a hard tech problem. Another hard tech problem, making a very level surface. So like, you have a flat table, but make it really flat, right? Like perfectly flat, like atomically flat. Also hard tech problem. And the robotics equivalent of this hard tech problem is a quiet robot. Like a robot that makes no noise, like a person. If I go like this, it's not going like, it's just quiet. And that's like sort of the hard tech problem in robotics.
And it's absolutely phenomenal, like how well 1X has achieved this thus far. Because it's like I've filmed with a ton of robots, and like my God, the thing is silent. Like it is mind-boggling. So you talk to Bernd, and then you're like kind of like, how does the discussion play out? Like, is it from day one you guys are talking about like, come lead all of AI for us? Like, what does that look like? How do you approach it, and how do you even break down the problem of being like, shit, how do I do AI for an entire robotics company?
Yeah, so I saw a great opportunity when I met Bernd because like there was this very beautiful teleoperation system where you could have humans control robots and do all kinds of tasks. And the really cool strategic element about a really good teleoperation system is that it tells you what the upper bound on capabilities is going to be once you have the AI. So if you can teleoperate a robot to do some cooking task, that's roughly what you can imagine the AI is able to do. And it really grounds your imagination and your planning in what you can actually serve before you've gone and built the AI system. So having a really good teleoperation system tells you what can we expect to get in the best possible case of AI. That's not strictly true. It is actually possible to do better than a human demonstration. But from a practical standpoint, humans are already very smart. So before you try to surpass the human, you should just sort of expect that like the first N years of your program will be basically just trying to get to that human level.
How does the conversation go with you and Bernd? Like, is that immediately you're like, okay, I want to take that approach to like the Tele-op is really good. Bernd showed me that. However, then that makes you decide to join.
That's right. Yeah. So afterwards, after I met Bernd, I was like, you guys have the best technology by far. I'd like to build an AI team for you and basically make a general purpose intelligence that goes really well with the hardware. And we align really well in a lot of the ways in which we think that the hardware and software should go together. We started charting out the AI strategy for the company, and that was 2 years ago. The strategy at the time has continued to hold today, which was we're basically going to collect a large amount of teleoperation data. We're going to pair them with the kind of data that is used to train chatbots today, which is language. And by combining the data of both robot actions and robot vision and language and really melding them together, you can now ask the robot to do anything you would like. And if the general purpose capability exists in your data collection and you're able to go and describe all of that in language, you can then now command it to do anything you like.
Yeah, and I saw this yesterday. You at some point were like, open the door, and then it went and opened the door, and you did this for a series of actions and tasks, and it doesn't take much imagination to imagine how you could say, open the door, go in the bathroom, or start taking a generalization like go clean the bathroom, and then it breaks it down into these subtasks like rather easily, especially with LLMs.
Yeah. So the LLMs became really mainstream, I think, in the end of 2022 when ChatGPT launched, and people could see that not only were the models useful for understanding text, but they could actually be used to automate many, many information processing tasks. And one of the really cool information processing tasks you can use with an LLM or maybe an LLM with vision is to break down tasks so that robots can execute them. And in fact, this was a work that I worked on with many colleagues at Google when I was still there, which is called Secant. And that was one of the first works that showed that you could actually use an LLM to sequence tasks at a high level. And if something goes wrong, you can go replan it because the LLM has the sort of general reasoning capabilities of a person. It's just sort of it lacks the other sensory modalities, right? It can't see, it can't hear, it can't touch. But if you're able to describe in words what has happened, it can generally reason about what it should do next. So, of course, today we have models that are much more powerful than that. We have models that can see, and as a consequence of being trained to both see and think, they can help robots visually plan. But it can go much further than that, right? Like if you have the data of not only seeing and thinking, but you have seeing, thinking, doing, then now your VLM, or I guess your VLM plus your actions, so I guess a VLAM is what some people call that, that might actually have the ability to do the whole see, think, or see, think, act, think, see again, right? And like now you get this really, really interesting capabilities emerging out of that, which is like these models can experiment with the world, get some feedback, refine their understanding of the world by actually testing their hypotheses physically. That's not something that current models have. But when you train models on the internet, they don't have that physicality, so they can't experience what it is to apply their beliefs to the world. But if you do have a model that is trained on data where you are repeatedly applying your beliefs to the world, you can start to build models that can now acquire knowledge on their own. And that's, I think, a capability that robotics and humanoids in particular will enable.
How do you sort of train models? Like, I know visual is a big part of it. How are you like taking and sort of merging other sensor data that like a robot might have? So like touch or other, I'm not aware of all the sensors on the 1X robot, but like on a technical level, how does that all sort of get merged and synthesized?
That's a great question. At a very high level, the recipe that has proven to work for the rest of deep learning is to cast the modeling problem as closely to a language prediction problem as possible. So in ChatGPT, the modeling problem is you have a sequence of text and you just predict the next text. And when you compress enough text this way, it will develop some sort of general intelligence. So the robotic analog of this is to basically turn all of your data, whether it's vision or touch or language or sound, into the equivalent of words, or I guess tokens is what they call them in language modeling, and apply the exact same training objective on all of this. The model does not actually care too much which tokens correspond to visual data and which tokens correspond to text data, because the architectures are so general that they'll find out any pattern between them, whether it's spatial or semantic or whatnot. Now, in practice, though, if you train a model this way, it is not necessarily going to be easily usable on a robot because a robot has to make decisions fairly quickly. And so you might want to make some changes there that would allow it to, let's say, process vision faster or compromise some ability to generate, but maybe it can perceive very well. And these are sort of architectural choices that we have to make in order to squeeze the model to run fast enough on the actual robot. But that's the general framework is basically the same as in language modeling, which is you lay out all of the data in a flat sequence and you just predict all of it.
Cool. Today for the demos that we've sort of filmed while Neo was at my apartment, it was pretty much all Tele-op. What is sort of the roadmap in the way you guys are thinking about taking it from a fully Tele-op system to one day a fully end-to-end in-home 95, 99%, whatever, autonomous system? What sort of has to happen? I know you mentioned at a high level, but are there any sort of further breakdowns you can talk about?
Yeah, so deploying in a consumer home is a very exciting but also scary proposition. And let me explain one way that it's extremely difficult compared to other robotic deployments. So in self-driving cars, you might build something that you call a data engine, which is that if something fails in the field, you go and collect more data for that scenario, and then you add it to your training data set. So the next time you encounter that, the problem doesn't happen again. That is easy to do because roads are public. So if you have some if you have some errors that happen in a particular unprotected left turn, you can just have your QA drivers go and drive there and gather that data. Or maybe your customers are gathering that data for you because they're driving on the road at scale, like maybe with Tesla's cars. However, if you try to apply this strategy in the home, it doesn't really work because you can't just go and knock on your customer's door and say, like, we know that the robot failed to make your omelet this morning. Can we go and practice making 10 omelets in your kitchen today so that we can make sure your 11th omelet is fine? That's like not really great, right? Like the customer expects that if they ask the robot to do something, it'll work. And if it doesn't work, then in the future, it'll work. So one challenge that we are working on solving right now is how do you, with very high degree of confidence, know that your model will be better at making omelets without actually testing it in the customer side? And this actually goes back to the prefrontal cortex we're training. So if you have a prefrontal cortex that could predict the future, and this is a powerful enough model that can get to the point where it's hallucinating what it's seeing, you could actually imagine that this model could be used to imagine what your robot would do in the customer kitchen without actually breaking the eggs and so forth. And so if your world model, so to speak, is good enough, then you can actually evaluate how good your system is before actually running it in the field. And that's really important for safety.
What are the barriers in the way of getting to that? Like, is that as simply like, oh, we just need enough, like just a few more H100s and like we a little bit more time? Or like, what's the delta between that and like thinking on an OpenAI or Llama level of like, we need lots of money and lots of training time and compute?
So the OpenAI and Llama levels of compute scale are truly astounding from the level of, bravery it takes to invest in something like that. And I think the robotics community sees that to get to general level robotics, we have to also go through a similar moment. The main difficulty in robotics from getting to that point is that it's actually really hard to measure capabilities. I can explain a little bit what I mean by this. This is actually really subtle and something that not a lot of non-roboticists even notice. So general purpose models like chatbots are evaluated on millions of different scenarios to get some sort of average guess as to how good it is. And this is how they rate which models are better than which other models. If you want to do the same thing for a robot, you have to try out millions of different tests on different omelets, different toilet tasks, different homes, and enumerate over many different kinds of diversity to get to the level of confidence in the capabilities of the system, right? So how much time does that take? Well, this is going to take years and years and years unless you have a massive fleet. But like, let's suppose you have one robot and you are running all these kind of evaluations. By the time you've finished running the evaluation, the world will have changed so much that if you go back and rerun the exact same experiment, you'll get a worse result. So robotics suffers from this problem where science is not really reproducible because it depends on this quantity which is always changing and not controlled for, which is the world. And it's very hard to do science if you cannot control all the variables. So when you're trying to deploy robots in general purpose environments and unstructured environments like homes, the homes will change. You cannot keep them fixed. And that means that until we can precisely measure how good robotic systems are, we cannot draw a very good, accurate plot of if I increase how much GPUs I'm training the model on, how much better does it get? Because we don't even know how much better it's getting if, let's say, if 7 days between when your first evaluation is done and your second evaluation is done, the world has changed so much that you really can't compare them because you're never really sure if the environment is the thing that explains the difference or whether it was some other experimental factor. To get to the ChatGPT moment in robotics, you have to first create the scaling laws of robotics. And right now, it's not very easy to make the scaling laws of robotics because we cannot accurately measure how good things are.
Before I ask what you think some of the robotic scaling laws could be, I'm still curious, like in terms of like what you guys think you need to train your sort of prefrontal cortex world model. Is that a capital problem for you guys, or is that like we need more compute time, or we can't even like get to that point yet? Like we really just need to figure out these like first principle scaling laws.
I think it's a mix of both some level of really insanely ambitious conviction that scaling will get better capabilities. I think that's what happened with OpenAI and folks at Google Brain who were daring to spend the compute even when it was not obvious that it would work. That's certainly one dimension of it. And the other part is that even at small scale, we can do a lot to improve the rigor with which we evaluate our systems. The error bars have to shrink quite a lot before we can be confident that when you 10x the compute, the difference in capabilities is actually meaningful. So I think this is sort of a thing that we're doing now. We're both scaling up our compute cluster because we're trying to really plan for success here. But we're also trying to do the small scale science to really make sure that when we're measuring capabilities, they're highly predictive of what actually happens in the real world. In addition to evaluation, which I feel like is the most difficult and pernicious problem in robotic scaling, there's also the question of how you count data. So in language models, you can draw a plot where as you increase data, the loss goes down. And this is counted very simply, which is just the number of tokens you visit during training. The tokenization strategy, of course, can change from model to model, but once you fix a tokenization, you can draw a plot that really predictably shows capabilities improving as you increase the number of tokens you train on. In robotics, what is a token? Well, it's a little bit hard to say. We know that there's a lot of redundancy in images. So if I have a camera that's recording images at 50 hertz, the top left corner of your image is going to look almost identical to the previous patch in your previous 50th of a second. And that's why video compression can get so many gains over image compression is because there's so much redundancy.
Interesting.
So if you just use a simple way to compress each image into a token, a set of tokens, you still have a lot of temporal redundancy. And also, many of the tokens don't matter that much for actually accomplishing robotic tasks, especially if the tokens have no influence on the robotic outcome, such as the sky or something. So there's a big question in robotics, which is like, how do you count how much data you actually have? Mm-hmm. If I have a robot that's in a factory doing exactly the same task over and over again, and I've logged a petabyte of this data, but it's doing the same task over and over again with almost no variation, you can't double count all of the data as extra data. It's really just like one log.
Yeah.
And so that's why also to get to robotic scaling, not only do we have to increase the volume of data, but we really have to push on the diversity of data so that there's as little redundancy as possible. But generally, we don't have a really standardized way to count data. And so we're also figuring that out at 1x, which is like, what is the right way to compress data so that we have this sort of similar token to improvement correspondence that we see in language modeling.
It sort of sounds like, correct me if I'm wrong, what you're generally saying is that like the data engine problem of just throw more data at it is not as effective as the quality and the diversity of data versus like the LLM approach is like just more. Whereas you're sort of saying more, yeah, but like better and more diverse too.
Exactly. So in robotics, it's extremely easy to collect a very undiverse data set. If you turn on your robot and let it autonomously run, it can generate a lot of data, but almost all of the data will look the same. And there will be almost no entropy in the data. In contrast, when you just have a scraper and you scrape the internet, by its very nature, the internet data is often very diverse. Although there can still be problems where if you're not careful with how you amass your internet corpus of data, you can still have a lot of data, but very little diversity. And in effect, that's not as much data as you think it is.
So what is sort of the like, maybe you guys don't even call it a data engine approach, but like what is sort of the data collection and I suppose engine approach to 1x?
Sure. At a high level, the data engine approach is that we have a foundation model that's been trained on many of our tasks. This can be anything from dancing with people to picking up blocks and stacking them to cleaning a kitchen to making a bed to helping an old person. Right? This is really varied and it really depends on what we're doing. We train a foundation model that has learned to see all these different experiences in this prefrontal cortex, which also doubles as our simulator. And from this, we now have this generalized understanding of the world. And we could then specialize that model into new capabilities. So for example, if you want your robot to do your dishes and for your specific home, we could take this model and specialize it to do that one task really well. But for example, by showing it a few demonstrations. What's really cool about 1X's approach here is that because every capability we're building is just driven purely by data, you don't need to write extra code to add those capabilities. So this means two things. One is that our capabilities are no longer bottlenecked by the number of AI researchers we have, but actually bottlenecked by how many people are collecting data for us. This could be operators that don't have a degree in computer science, but this could also be users like yourself who may not necessarily want to write code, right, to increase capabilities. And so I think that to get to really general purpose systems, you really need to get to that point where you're not writing new code to add new tasks. And that's really essential to the DNA of our data engine, is this system where you want to be able to add new skills without having to write code. Andrej Karpathy, when he was the director of vision at Tesla Autopilot, had this catchphrase he called Operation Vacation, which was they wanted to get to the point where the Tesla autonomy could be improved while the Tesla AI team would go and sip margaritas on vacation, right? Like some program manager who wasn't on the Autopilot team could basically turn the crank of the data engine and improve capabilities only using data and not having to write more code to build the system. And so we embody that same philosophy at 1X, where we want to get to the point where the AI team can go sip margaritas and the capabilities improve without us doing anything.
I'm not sure like there's even an official name for this yet or like a total complete protocol on your end, but one of the favorite and most exciting things I think you guys are thinking about developing is the ability for in-home users to train their own stuff. How are you guys thinking about that? Like, how is it as simple as sort of like kind of like a crappy camcorder Windows software editor where like you say, okay, like start like inputting data, stop outputting it, and then you like the user can prompt the robot or teleoperate it to do like a specific set, like giving you a Gatorade bottle from a weird part of the like place where Gatorade bottles are kept or whatever. How might that user training process like look like in the end?
We think that the only way to get to a large number of general purpose capabilities is to build a system where anybody can add tasks. Because if you don't do that, then the capability ramp up you have is limited to the number of people who can write code, which is too small of a number. So we don't know with perfect clarity what the interface for adding skills yet for the consumer will be. But one intuition you can think about is that it's kind of like those toys where you can press a button and you record your voice and then it dances to your voice. So think about it as almost like a smart recorder where you show it a few times, this recording, and it plays it back, but it plays it back in a smart way, right? So if your egg is not positioned exactly where you want it to be, it will still record the kind of general understanding of the task, not the actual arm motions that you recorded during the demonstrations. So we basically want to build a system that's kind of like monkey see, monkey do, but it generalizes to small changes in the environment when you are actually using it. Because the home is always changing. You cannot expect everything is always in the same place.
My Gatorade will not always be in the same place. That makes a lot of sense. What are some of the hardest parts? I sort of hesitate asking this question because I'm like, there's probably quite a few hard parts. But in your mind, what are some of the hardest parts about going from where we are today to like a very solved, like perfect Neo, like just does everything perfectly in an insanely high level?
Yeah, so robotics is one of those very difficult but also exciting problem domains because it encompasses pretty much every possible problem in computer science and below. It's really an integrated systems problem. And I can speak to just like one of the many problems we're tackling in addition to evaluation. And one of them is just like imitation learning today in robotics is not actually as strong as what most people think. You see a lot of really cool demos. We put out a few where robots could do really exciting general purpose tasks. And I would say that the current state of imitation learning techniques are much closer to a replay than a generalized understanding of the task. So, for example, if I teach a robot to fold a shirt, it can do that, and I can even move the shirt around a little bit with, like, let's say a few centimeters here and there. But if I transplant that system to a completely new table height or a completely different shirt, it won't really understand how to take the knowledge from the demos and generalize to a much more different scenario. So in a very, this is not exactly true, but like in a somewhat reductive sense, you can think about our current state of robotic learning as much closer to just replaying what it's doing during collection than generalizing to new scenarios. That being said, there's been a lot of really exciting work both internally at 1X and also externally where you can start to see some signs of life where when you collect some data and you fine-tune your model on a very powerful foundation model, the general knowledge in the foundation model does confer some more deep understanding that is not present in your demonstrations. For example, if like your demos are collected during the daytime, but then you want it to fold your shirt at night, the knowledge in these kind of pre-trained foundation models can let it generalize to that in a way that's not so robotic and only doing exactly what you're training it to do.
That makes a lot of sense. Earlier you mentioned the idea of a data sponge. Can you talk a little bit about that?
This is a design principle I believe very strongly in, and it guides how I architect the neural networks on the AI team at 1X. So in machine learning, there's a lot of ideas trying to make neural networks better, right? Like by default, they have a lot of problems generalizing or reasoning, or maybe they don't have inductive biases that you can build in that make them more sample efficient. In the process of trying to make models better, a lot of times researchers add ideas that reduce the amount of data you need to train it, but at the same time that you do this, introduces an optimization bottleneck in the model somewhere. So for example, let's say I add a special network at the end of my transformer that makes it easier to predict actions so that the robot is better at doing actions. And this works, but then now I want to scale up the model. I want to scale up the data, I want to scale up the parameters, I want to scale up the compute, as people do in scaling laws. If you're not careful, it's very easy to add a component to a neural network that slows down the ability for the rest of the network as it's backpropagating the gradients from the end to the start. It is slowing down its ability to absorb information.
Right.
So what seems like a good idea at a small scale might actually be a thing that increases the number of optimization steps you take by 3 to 5 to 10x at larger scale. Now, at that larger scale, like we're talking about millions of dollars of compute, right, in terms of training a big model. If your clever idea that made your model more sample efficient slows down the ability to sponge up data by 10x, that's a 10x cost on training a foundation model. And that's like not acceptable, right? Like these models are already very pricey. So that's why the transformer architecture has been so revolutionary, is that it's an architecture that has not only been really good at solving problems like temporal credit assignment, but it also has very few optimization bottlenecks when you scale it up. As you make the model bigger, it doesn't have any parts in it that slow down the propagation of gradients to the earlier layers. In robotic learning, you see a lot of papers that propose extensions to these ideas, to these models, like, let's add something to a transformer to make it smarter. But if you were to make the transformer bigger, the gradients get flow to the transformer slower. And then now this is sort of an engineering trade-off, like, do you want the sample efficiency at the cost of 2x the cost to train? And often at very large scale, that doesn't work.
To sort of change topic a bit, what does the general makeup of the AI team at 1X look like?
The AI team at 1X is composed of a lot of people from self-driving car companies like Tesla, Waymo, Cruise, Neuro, as well as people from robotics programs like CMU and Fair Robotics, as well as Google DeepMind, and also people who are hungry and eager to learn more about getting into robotics because they see how exciting and challenging humanoid robotics can be, and I think it's potentially the next big thing. So what we select for on the AI team is basically a team of generalists who are willing to do anything to make the robot work. And we build everything from the data engine to the web tools to making sure the internet connection is fast enough in the office.
So on the actual AI engineering side, what's going on?
Yeah, the main thrusts that we're doing on the AI side are solving the evaluation problem so that we can build scaling laws and building better foundation models that confer more generalized knowledge to our models. When we fine-tune them, we want to make sure that they're not just replaying the demonstrations in a somewhat dumb way, but they're actually pretty smart about combining knowledge from the foundation model with the new information that you've shown in the demonstration.
A final question I'll ask about that before asking you some fun questions, I think would be like, how do you guys think about the safety side of things? Obviously, AI safety and alignment is a big idea in general, but for you guys, it's very specific. And like, you're putting systems that are doing things on a robot. And like, we talked a lot with Bernd about how safe it just is from mechanical first principles, which is cool. But beyond that, do you guys have to think about that much on the software side?
Yeah, safety is a AGI hard problem in the sense that you do need a very general intelligence to understand how to be safe in all kinds of contexts. And this is assuming already you're mechanically safe, like Bernd described. For example, there's a very common routine that we do, which is that we want to reset the robot to some sort of known static pose with the arms at its side. It really, depending on the situation, you may or may not want to do that. For example, if you are holding a door handle and you want to go to your default pose, if your hand is stuck, you really don't want to do that because you're going to end up pulling yourself to the floor if you do this. So if your arms are high up in a shelf and there's a bunch of things that are sort of obstructing your wrists, you got to be really careful about how you extricate your wrists from the shelf and then bring them back down. And those are some just very basic everyday things, right? So to solve safety, we think that taking a very generalized approach to just in the same way that we add capabilities is the right way to go. We treat safety capabilities as no different than all the other capabilities you do, like pick and place and whatever. I take a lot of inspiration from how language model companies do safety. One way they do it is this kind of post-training phase where you teach the robot to reject improper requests that would lead to unsafe situations. You teach the robot to generally steer away from unsafe situations. And it's hard to define safety. So like it is to define cats or define anything really in the real world. And so by having humans provide the data around what is safe and what is not safe, we think that we can build this general model that has the right intuition of how to behave in any given setting. We have some cool signs of life here where, for example, in the most simple task possible of just driving around randomly, making sure not to bump into walls and obstacles is really important. When you are interacting with other people, you have to have a bit of common sense of the theory of mind, and that's where safety actually gets really complicated because in order to behave safely, you need to basically predict the behavior of many other intelligent agents.
I know it's no longer what you're doing is directly at 1X, but I'd love to nerd out a little bit about bio.
Yeah, sure.
I think it's probably out of all the companies I've gotten to feature on S3 and the different kind of fields they're in, bio is the most underrated and seemingly most exciting in the next century, behind humanoid robotics in general. I would actually jokingly say, but seriously also mean. I'm curious, like what sort of bio research or companies or frontiers you're really excited about right now.
Yeah. One intersection between humanoid robotics and bio is the building a lab in a cloud. So it turns out that there's a lot of science in the world, like for example, building the fly connectome, which is the whole wiring diagram of the fly brain, that is really painstakingly slow because a lot of grad students have to share a special electron microscope that is only present in a couple labs in the world. And the coordination is just super slow and difficult. And you have to kind of shave off little wafers of fly brain to image all of it. And it's very painstaking. You need a special grad student who knows how to speak the magic words to the microscope to make it work. If you could move all the expensive scientific equipment in the world into one location in like a warehouse in Tennessee and have people just teleoperate Neos, then you could really reduce the cost of science by basically having everyone remotely operate things. This hasn't been possible before because people often only build lab automation when there's an experiment that can be large scale enough to justify a specialized machine, for example, PCR or sequencing, or things like that. But if you want to do just general basic experimental science, if you have the ability to just remote into a embodied agent that can do anything a human can do, you could just put all the expensive bio equipment in the world in one place, co-locate it all like a data center, and then you save money on science, and people can basically do shifts around the clock to do science, and you don't have to drive over to the lab to take care of your yeast growing in a petri dish.
That's so cool. I can't wait to do an S3 follow-up at like the 1X, like the cloud lab. Like that's super cool. You guys must be really excited about that.
We have many ambitions in other verticalized industries, but the home comes first.
In terms of like getting a little bit back to bio, I'm personally really curious about like how little we understand about how the human brain works and mapping it with computers. And obviously there are brain-machine interfaces, and people are starting to think about neural interfaces or even like nervous interfaces. I'm curious sort of what your take or view on that field right now is, and specifically on the neuroscience angle, because I know that's what you thought about a lot, and it seems very unsolved, which is exciting.
I think we're about to see a lot of really interesting breakthroughs in BCI devices that can read muscle intents and, to some extent, thoughts from people. Not with the level of fidelity that you see in sci-fi movies, but enough to create really interesting, compelling experiences to control devices and potentially even receive inputs back. Obviously, we are in the business of trying to control robots remotely and embody a human in a robot, so this kind of technology is really interesting to us. On the brain simulation side, I do think that the brain continues to be really complex, and it's interesting that there's so many different levels of abstraction to try to study a brain, either from the sort of cognitive, dynamic side of things or the low-level biophysics of things. But to date, it seems like what is really missing is our understanding of how to build brains the way brains are, rather than just build machine learning systems that can approximate the behavior of brains. There's still this very difficult grand challenge of like, how do you replicate the simulation of a brain in this sort of full fidelity? That seems still very far away, and I don't see an easy approach to do it. It seems like to me that in order to crack that problem, you actually might need to not only build the brain, but you need to build the rest of the world around it. Because otherwise the brain wouldn't develop properly.
Oh, I see. Like you can't just build in a box.
Yes. So it's like brains only form correctly if they're in the environment. So like even if we had the computing resources to simulate a brain, I think it's possible that you need to simulate the blood, you need to simulate the muscles, you need to simulate the stimuli into the brain, you need to simulate the brain's parent, the brain's nemesis, the competitors. How do you simulate like sexual reproduction between animals? And you can kind of keep going on in there, like the if you give a mouse a cookie kind of story. And I think in the most pessimistic case, evolving brains in silico requires actually simulating all of life, not just the sort of construct of a connectome.
What is the value of being able to replicate a brain in silicon versus like just doing it organically?
It is much easier to reproduce experiments with silicon computers. One fun fact about neuromorphic computers, which are often analog, is that if you put your thumb on the chip, it changes your results. So
that's cool.
The thermals of your finger will actually change the analog computation. And if you lack the ability to faithfully reproduce an experiment you ran yesterday, progress is so much slower. Like I would say that the progress in computing has been only possible because the von Neumann digital architecture is designed so that you can get the same exact experimental result with the same inputs. The determinism of computers makes it possible for us to do science. If you don't have that, you're stuck in the same land that robotics is in, which is that you run an experiment today on Monday. On Friday, you have a new idea, and let's say you have a different measurement from that result, that experiment, but you don't know if the difference is because it's Friday or if it's because the idea is different.
Oh, that's interesting. Yeah, that is quite cool, and that makes sense why it's valuable to try to simulate a brain with binary versus even analog or even organically.
There's many reasons why analog is better for many reasons, and in fact, in the limit of things, analog is the most energy efficient way to build a computer. The main challenge is that it's hard to iterate on the system. So I think as an engineer, you have to make the very conscious choice of, do you want something that's more ideal or something that's easier to iterate on? And I think that's a choice that a lot of technologists have to really make a hard compromise between when they're trying to build an ambitious system.
This next question's a little weird, but I like asking people who are building exciting things this. And the question is like, can you try to describe how you think your brain works? Actually, probably the best segue ever considering what we were just talking about, by the way, because that is how I word that question every time.
I'm a chronic procrastinator, so I know personally that my brain operates a lot on guilt of not completing a task that I started. And I have all sorts of ideas that I work on, and I usually focus my energy on the thing that I'm most guilty about at any given time. That works, I guess. I also think that, like all people, I'm a creature of habit. So the way I think is often reinforced by how I thought before. it's very useful. Humans are very good, self-reinforcing agents, and so I think you can think your way into really hard work ethics. You can think your way into being creative. I like to think about the brain like a muscle, like any other system in the body, and it's a system where if you repeatedly use it for some task, it'll get more energy efficient at doing that task, and it'll optimize itself. So if you want to be creative, you could just spend more time doing creative things. If you want to be hardworking, you could just get your brain used to working really hard. And I think I'm a creature of habit, so to kind of make robotics work, I spend a lot of time writing and thinking about robotics, and that makes it easier to think about robotics in the future.
I think it's sort of interesting how bad we are at sort of controlling ourselves. It's like, I feel like recently humanity's beginning to realize, we can optimize ourselves, and yet we still really suck at it. Like, it's not like, as like sometimes I'm like, oh, I need to go get this done, or even I would like to go do this thing, but I will procrastinate for weeks or months, or not just not do it, or whatever. I always wonder like why this is. It's like, is it just a battle between like our ego or superego or whatever, or like those aren't even real things? Those are just philosophical.
I think the brain is an energy expenditure minimization machine. Mm-hmm. So if your brain is working really hard to do some task, it will find ways to add shortcuts to make the next time you do the task easier. And that's like one of those it's like out of laziness, you can actually do a lot.
What's something you know or believe that you think other people might not, or might not very commonly?
There's something called Conway's law, which is that organizations often mirror the products and that they make. So products mirror the communication structures of the organizations that make them. You see this very commonly in robotics, actually. So, for example, in many robotics companies, there is a team that works on perception, a team that works on planning, a team that works on control, and a biz dev team, and a product team, and a designer. And this is sort of your typical breakdown of like a robotics team. And I guess for the technical side of things, it's often this very clear pipeline of perception, planning, control, and so forth. The organizational architecture of your team will directly influence the thing you end up shipping. So I think something that's very overlooked that I believe very, very strongly in is that a team should structure the org chart to look exactly like the thing they're making. In this age of AI, if you're trying to make end-to-end models, I think building a org chart where there are separate components that kind of fold into one big thing doesn't make much sense. You should actually build your team like a sort of undifferentiated neural network that reflects the system you're trying to build.
Interesting. I wonder how far down the literal path you can take that for your average company.
So I've heard the rumor that an unnamed large language model startup is scaling up their compute, and in doing so, they're having to really optimize latency between components of their model. So you can think about their data center building being the same architectural layout as a neural network, to make sure that the pieces are minimizing latency to each other.
I've heard this as well, which it makes sense. It's the same idea as having really great internet and being really close to the stock exchange.
So once your building looks like a neural network, well, where are the people going to sit? Well, so now your office layout starts to look like the layers in a neural network, and eventually this Conway's law becomes manifested physically because of the compute backbone of whatever LLM you're trying to make.
It's thinking deeply about Conway's law that is sort of the one path I sort of start mentally nodding with the common Elonism of simulation theory. Most of the times, out of context, I'm don't love talking about simulation theory, but as soon as you start thinking about this, you're it gets quite interesting quite quickly. I'm curious, sort of in that sci-fi realm, simulation theory or laying out your people where the building structure is and the shape of a neural network. What some of your favorite sci-fi stories are?
I'm a big fan of Black Mirror in the way that it makes you think. I'm also actually lately I read this book by called Clara and the Sun, which is by Kazuo Ishiguro. It's about this home robot or artificial friend that gets purchased by this family in the future, and there's genetic engineering in the future, and it's very sci-fi, but it's told from the perspective of the robot that's very innocent and naive. And it's really a story about humanity. So the robot is very naive, and through its narration makes a lot of innocent observations about how people behave to each other and how they behave to robots. It's not at all about like technology. The book doesn't go into the technical aspects of it. But I do think that like when you build humanoid robots or when you build AGI, it'll be profoundly interesting from a cultural and sociological and even religious perspective, because it is a mirror to who we are as people, less so than it is about like how was it implemented, or like what is the choice of actuator you use, or are you using like silicon or analog or whatever. It's like, but the most interesting thing to me is like once you create these things, they will reveal so much more about humanity to us than we knew, at least consciously.
That's super cool. Yeah. And it's all very similar to what we were talking about with Conway's law, and sort of like the output product like very closely mirroring the organizational structure, or in some cases like now it's becoming the reverse.
They influence each other, right?
Yeah.
So like if you want a particular org structure, you can try to do this using HR, but you can also try to do this using software. So you can actually influence the org structure by refactoring your software, and that will percolate to the org. And vice versa. If you want to refactor your code base, you can also refactor the organization. And those changes really are in sync with each other.
My last question for you is also a little bit odd to ask, but I think it's super interesting when you're talking to people who are working on pretty insane systems and things that'll impact humanity. And it's how would you describe your current life philosophy?
So at 1X, I think we're trying to do something really daring, which is bring a humanoid robot to the home market way sooner and ahead of schedule than what most other well-informed experts would think. And that is not without risk, right? Like other people have very good reasons as to why this may not work. But I do think that instead of taking a long time to do it and potentially, wasting a career of 5 to 10 years preparing for a reasonable timeline, it's much better to push for an aggressive timeline where you find out whether the idea will work or not. You fail fast. And in the worst possible case, you learn a lot about why something doesn't work, and you move on. But I think that in the case that it does work, then you basically have so much alpha because you're 10 years ahead of what everyone else thinks is possible. And I think the most interesting opportunities in life happen when you have alpha that something is early way before other people do. So in some sense, I think the bet on humanoid robots is one way to manifest this. But more generally, I do think that like when people want to make decisions in life, you can think about like, is the upside of being right is just so much bigger than the downside of being wrong. And I think for many people who are in technology, that this is often the case.
Fantastic. Well, I love that answer. And thank you for this entire interview. This is like probably the most in-depth AI one I've ever done. And I don't know, I had a lot of fun and learned a lot. So
well, I'm really grateful you had me on the show. Yeah, thanks for you've monopolized the world's supply of home humanoid robots today.
This is true. I'm honored. Thank you for bringing Neo, and thanks for building 1X.
Thanks.
This is great. Oh my gosh. So good.